Hello, everyone. We'll still give a minute maybe for other people to join. Putting here in the chat a link to the notebook that I'm going over. It was also in Slack. And as I mentioned in Slack as well, if you would like, there's some of this is going to be sort of live coding, like me going through things if you'd like to follow along too. Be a good idea to open up either like a new blank Google Colab notebook or start a notebook yourself in whatever you like to do that with locally or otherwise. Colab is nice because it already has PyTorch installed and it's just in a browser, but it's just going to be for funsies.
Quick question, Cole. If I just made a copy of that notebook in my own Google Drive, will that mess up anything on your end, or that should be independent, right?
Yeah, it's independent. Like the link that I shared has viewing permissions, so to edit it, you would have to make a copy of it.
Got it. Okay, thanks.
Yep, great question. So, all right, I'll go ahead and I guess get started. So, welcome everyone. Today we are talking about deep learning things. I'm specifically going to be going over PyTorch, which is a very prevalent framework for doing deep learning work in Python. There are other ones. The things that we're talking about really translate to sort of any framework. So like the specifics of like doing something in PyTorch are less important and they're more practical, but ultimately we're going to be going over like what the things are. Like when you're talking about a neural network, what are the different pieces of it? How would you get up and running with it, etc. And it'll be a fun time. So this is the notebook that I shared already. It's in Slack and the Zoom chat right now. As well, like I was just saying, it would be helpful to have just like an more or less blank notebook to be following along with some things, but that is up to you. So really quickly here, the sort of building block for all deep learning is really the numbers, and specifically collections of numbers referred to as tensors. So a tensor is effectively a multidimensional array. It can actually be any number of dimensions, including 0, like a single number can be wrapped as a tensor and used there. If you have a one-dimensional array of numbers, such as this, it's also called a tensor. We would more intuitively refer to it as a vector. If you have a two-dimensional one, we normally talk about that as a matrix. A matrix is also a tensor. So all tensors. The things you can do with them are very similar to what you could do in, say, NumPy. So NumPy arrays, NumPy ND arrays, and Torch tensors, or TensorFlow tensors, or anything else like that, are effectively the same. So right here are some examples of stuff that you can do with them, but I really want to get in to start playing with these directly. So we come over to an empty notebook such as this. At a minimum, you'll want to, if you're using Google Colab, you'll want to make sure that up in the top, this if you're not already connected, there's a button that will say connect. Otherwise, you can come up here and say restart runtime to make sure that you have an active kernel going. Once that's there, the first thing that we're going to need is to have access to PyTorch. So you can go ahead and import PyTorch here. And then I'll just add down here, we can start playing around with some stuff. So let me just start out with getting a random tensor just to look at it. So torch.randn is a very common thing to use, especially for demonstration purposes. There's actual practical uses for it too. But what this does is it will create a random tensor. The n means it's normally distributed, so every value in it will be, mean 0 standard deviation 1 sampled from that. And we provide it with the dimensions we want this tensor to be. So I could put 1 here and then run that and see what happens. So is this big enough, by the way? Anyone like to make it bigger? Like me to make it bigger? I'll make it bigger anyway. So what we've done here is effectively we have a list or an array tensor of size 1 with a random number in it. If you run it again, you get a different random number. Sometimes they'll be positive, sometimes they'll be negative. It's sampled from a normal distribution, right? So we can do other things like we can get 2 of them. And so and NumPy again has very, I think almost the same method name for a similar thing. So there's that. We can also get multi-dimensional ones of this. So instead of having a 2 wide one-dimensional tensor, we can say have a 2 by 2 matrix now of random numbers, and so on. And you can keep doing this as much as you want, and these don't have to have 2. You don't have to only have 2. I'm just doing that so that it fits on the screen. But so this is a 5-dimensional tensor where every dimension is of length 2 in that case. Ultimately just makes a very difficult to visually parse list of numbers, right? I mean, it's useful to work with. You don't normally look at them like this, though. It keeps printing down there. So look at here. Let's say that I am going to save that into a variable now, and I can do some stuff with it. So like if I print x dot size, for instance. So size is how we look at the size of the tensor, and it will be the same dimensions in this case that we gave it there. Yep. So like there are, like, if you're getting these from somewhere else, it's useful to be able to get the size from things, especially like, let me put this into something a little bit nicer to work with right there. You could also, if you want, there are sometimes you need to be able to like unpack the size. So you say like, what's the dimension that's being used here? So I can say like height and width equals x dot size here. And then go ahead and like print out width and height right there. And they're both 2, so that's not super useful, but you can see they're the same. I unpacked it in this order. I printed it in the opposite order. That's why they're in a different order, if that wasn't clear. But so this is like, these are some things that you would do here. Now, getting to something actually practical. The backbone of deep learning is effectively matrix multiplication. And that's why tensors are such an important part of the whole thing. I mean, even with frameworks like TensorFlow, tensor is right there in the name. So ultimately, what we're trying to do usually is fancy linear regression. It's the fancy part is because it ends up not being linear, but we'll start out with something here where, like, I'm going to say, well, usually you're taking some sort of input features and you're trying to predict something in output features. So the, like, if we were going to do this as just a straight up line, for instance. So let me set up some stuff. So like in dim equals 1, out dim equals 1. We'll use these. So then I'm going to say that my x is torch.rand n in dim, and then my w equals torch.rand n in dim out. If I spell correctly, in dim and out dim. So, and I'm going to put a 1 right here, and I'll explain why later. For now, just it makes it easier for me to write things the way that I'm going to write it here. So then if I was to say here, like y equals x, and then the at sign and w, where like at is effectively, if you've seen this in NumPy, it's exactly the same thing. It's basically like matrix multiplication. And then so print y dot size. I should be happy now. Okay, So all of this ends up giving me that. But before we get to like why I would have that, let me add one more thing here. B equals for dot brand and 1 of n plus b. Okay, so looking at this line right here, does this equation look familiar to anyone? Yeah, what's it the equation for?
Line.
Exactly. So when I said earlier that we're basically doing fancy linear regression, we are. This is the backbone of everything in deep learning. Period. Full stop. There's a lot of stuff that goes beyond that. Specifically, we'll get into the specifics later. But one of the things that you can do with this, like, is this, since these are all one in, one out, basically, this is just a single line. You could do this with multiple lines at the same time, right? So if I was to say, like, I have 3 values as an input and 2 values as an output, and I run this, you can see I get 2 as my output here. The 1 is because I added the 1 right here. I'll get to why I did that later again. But the fact that I had, let me print this. Whoops. Slides. And then just making it so that I can print the shapes of these things as I'm going. So my X is a 1 by 3, my W is a 3 by 2, B is a 1 by 2, and my output is a 1 by 2. So anyone know why we're able to go from a 3 to a 2, 3 input to a 2 output here, based on like the operations we're doing here?
X times W will be 1 times 3. Oh, sorry, 1 times 2. Then plus B will still be 1 times 2, the dimension.
Yeah. So the basic the important piece is right here. This x at W. So this is matrix multiplication. So we have in this case X is a 1 by 3. And you're multiplying it by a 3 by 2. So the result is a 1 by 2. So it's in N by D matrix input, a D by M matrix, and then you end up with an N by M matrix at the end. All right, so standard matrix multiplication. Now, another way sort of to think about this is we're changing the size, like we're writing a function to change from like this set of numbers to this other set of numbers, and the sizes can be different. Now, reasons why you might want to do that, like you could, if we're talking about predicting a shape, like what shape is in an image, like I can predict circles, squares, and triangles, let's say. My output that I would want would be of size 3, because like you can imagine this being, I'm going to predict a 1 hot of like, so if it's a circle, it's 1 0 0, if it's a square, it's 0 1 0, and if it's a triangle, it's 0 0 1. That would be like the output we're trying to get. And my input would be like the dimensions of an image. So like if it's a 10 by 10 image, 10 pixels by 10 pixels, it's 100 in. So like, let's say that I'm trying to fake that. So I said I have 3 outputs and then I have 100 inputs. This all still works fine. So 100 in, 3 out. And then the magic of like actually predicting it would be if my W was the right numbers to make it so that the output would end up being one of my 1 hot vectors that I was just talking about in 3 dimensions. So any questions? Did that make sense?
So the application of this is in images is.
Well, it could be anything, but yes.
Got it. Okay.
Yeah, I was just saying for example, like conceptually, if you were going to write a computer vision model or anything else, right? Like what you have to do to get it into like deep learning land is your input has to be numbers and your output has to be numbers. And then the way that you work with it is like pixels, for instance. Let's say that we're talking a grayscale image. So every value or every pixel is a value between 0 and 1, where 0 is black and 1 is white, and it's gray in the middle. If I have a 10 by 10 image, which is really tiny, right? I can imagine flattening that out into being 100 wide list of numbers, all between 0 and 1. So then that's my input. What I'm trying to get as an output is like a categorical vector that says like basically the probability of it being a circle, a square, or a triangle in this example. So then the thing that does that is this W in the equation. Right, so this thing is taking my input features. It takes something of input feature size and output something of output feature size. And then how it gets that is like just matrix multiplication. Like you're just multiplying all of the input values and then like, you know, by columns and then summing rows. Right. Yeah. So that's, I mean, there's more to it, but that's like effectively the operation. And then we're stacking lots of things like this together. Additionally, why I put this B here. Well, what does B represent when you're doing this just normal linear regression? What's it for?
It's the intercept.
Intercept.
Yep. Also referred to as the bias, which is where the B actually comes from. I never knew that until like, you know, they tell you this in like elementary or middle school, and then they don't tell you what B means until you get into data science. It's the bias, right? Yep. That is the intercept.
Bias, like if this were like an interview question, right? What does that mean in like this context?
Yeah, so if you were just multiplying, your intercept is 0, right? So you can only like scale magnitude up and down, like, but you can't say like if I'm predicting a value of 0 or 1, then like that's one thing. But it's saying that like I'm starting as a default of 0, and I have to be convinced like multiply by a high number to get to 1. Versus like, what if this particular output like has a probability, like just a baseline prior probability of being closer to 1, right? So I would add a bias so that I have to multiply it by a much smaller number to get it closer to 0. It defaults to being closer to 1 in that example. It pushes your probability, like your output value, it can be a probability or not, closer to a particular value.
Okay, thanks.
Yeah, and then this, so the bias vector in this case is always the size of the output dimension for this. So like whatever you have a per output feature intercept effectively. So this is the, like I said, the basic building block for this. Now, if I actually look at, instead of printing the size here, let me actually print the value. And this is random, so it'll be whatever. Let me actually do it again. All right. Yeah, so here, this is what I'm getting, right? So imagine, again, we're predicting a square, circle, or triangle from an image that's really small. How would we interpret this like as a person? Like what would we say the prediction is if this were working properly? If it's a square, circle, triangle in that order. Like, do we know what the model would be telling us the prediction, the results? Yeah, it's going to be the highest one. At least that's what we would try to make it be. So like, again, if our targets we're turning our 3 categories of circle, square, triangle, I'm trying to keep them in the same order every time. We're turning those into vectors. So it's like, if it's circle, it's 1, 0, 0 is what we want. If it's square, it's 0, 1, 0. And if it's triangle, it's 0, 0, 1. These things don't output exactly only 0 or only 1. They output continuous values. But you would interpret it as like the highest one is the one that it is. So this says like very low chance of it being a circle, very high chance of it being a square, and like medium chance of it being a triangle would be a way to sort of turn this into a sentence.
Is the range like -10 to 10? Like negative, like it's a not likely at all, and a 10 meaning it's like super likely that this is what it is in the order?
Right now it's arbitrary, because
Okay.
I'm just taking like a random, vector and multiplying it by a random matrix and then adding a random vector. So it's like whatever the rand n outputs normally distributed values. So it's mean 0, standard deviation of 1. They can, that with low probability, it can be really large positive or negative numbers. So the actual values here like don't so much matter. It's just interpreting what they mean is the main goal.
Got it.
Right. So this is again the basics of this. There's usually with these things, there's two main components to any neural network. One is everything we've seen here, which is matrix multiplication, and the other is what's called a nonlinearity, or also called an activation function. People say those interchangeably. And what this sort of means is instead of outputting purely continuous values, because right now you have the question of what are these magnitudes and all of that, you want some way of kind of approximating these as sort of like Booleans or binary values, or just generally you're trying to say like something is on or off, right? So one common way to do this is a function called a sigmoid, which is effectively like an S-curve. It takes your input, it squashes it to the range of 0 to 1, where like the closer you get to 0, like lower values approach 0 slower. It's somewhat linear in the middle, and then as you get higher, it like approaches 1 slower. So if I run this now, see all these values are no longer in some crazy range. They're all somewhere between 0 and 1. And I can keep running it. Ignore the scientific notation. These are all extremely low. Right? But all of them are in the same 0 to 1 range. And that's what, in this case, the sigmoid function is doing. So it's, again, like just an S-curve, actually. Yeah.
And that's called a activation function, you said?
Yeah. It's an activation function, also referred to as a nonlinearity, because it makes the result nonlinear. Like this is it's an S-curve, it has curviness to it, it's not a line, so it is nonlinear.
Like in logistic regression.
Exactly, yeah, it's the same exact thing. Yeah, so again, that's what we're looking at right there. And actually here, this is a good example or a diagram of exactly what we just did. So you're going to have, let me make this smaller. You have your input features here. This sum right here, this is the matrix multiplication. It's just written as a summation instead, and then applying the sigmoid function right here, and that gives you your output. We just did exactly that. Yes. All right. Now there are other activations and sort of like, I think this one is actually built in here without importing anything else.
So, sorry, quick question.
Yes.
Similarly to logistic regression, you would, in a neural net situation, you'd only want to use the sigmoid activation function if you were trying to predict a binary or
between 0 and 1, yeah.
Okay.
Yeah. So one other activation that's pretty common is this thing called ReLU, which is short for rectified linear unit. It's a fancier name than it actually is. What it is it's exactly max 0 y. This is ReLU. So what it means is like for your input, if it's 0 or lower, it will output 0. If it's higher than 0, it outputs the value. So it's like a flat below 0 and then linear above. So like oftentimes like you'll see ReLU all over the place if you're reading anything about neural networks. Like most of the activations sort of in the middle of a network will be ReLU. And there's the reason is because it's well, so it's linear, so it lets things sort of scale arbitrarily, which can be useful in certain cases. The reason why you want the plateau of like if it's below 0, it's 0, is you're thinking about turning outputs on and off. So if it's below 0, it's off, and it's always off. You can't like scale things negatively in that case. And if it's on, you have the ability to scale it linearly. Sigmoid, you can do the same thing, because if it's outputting 0, like the lower the values, it's just approaching 0, and the higher the values, it's approaching 1. You just are limited to how much you can scale something. Back in the day, like sigmoid was used throughout like neural networks, but then there was research showing that it's like the squashingness of that was sort of limiting its the expressive power internally to the model. So that's when they started coming up with things like ReLU to allow it to, like, you can scale big if you really want. Typically on your output is where you'll use something like sigmoid if you're, again, trying to squash to 0 to 1. There's another one that's common, usually as an output, which is tanh. And tanh squashes between -1 and 1 in the same way that sigmoid does. So you can think of it as just like a sigmoid between -1 and 1. It's the same S-curve shape. So the choice there just depends on what you're trying to do. If you want a -1 to 1 range or a 0 to 1 range, you pick the appropriate one. Otherwise, most of the time, something like ReLU is what you would do there. Now, where this starts getting more interesting is this, what we have right here would be referred to as a perceptron. Fancy name from, I want to say, the 1950s. So the first things that they were trying to do with this was having machines that were trying to guess a shape given some input pixels. And that's why I use that example of circle, square, triangle, where you can do this pretty well with a single matrix, optionally a bias vector at the end of it, and then just like sigmoid effectively. What you can't do beyond that is anything where sort of the outputs are sort of exclusive or whatever. So I actually have a diagram of something else, like a common task to prove that your model can do like anything is to solve a nonlinear problem. And one of those is the operation XOR for Boolean values. Does anyone know XOR? Or can anyone explain XOR to me? Well, I have it right here too. So with binary values, there's three, like the two common operators that I'm sure you've all seen, especially if you've written an F statement, are and OR, right? So like this here is the truth table for and. So given a true and true, you get true. Any other combination, you get false, right? So both inputs must be true to output true. For OR, both values have, if both values are false, you get false. Otherwise, you get true, right? So exclusive OR or XOR is somewhere in the middle. It says both values have to be different to get true. That's why it's exclusive OR. If they're both true, you output false, and if they're both false, you also output false. So with this, I'm going to show this in sort of a weird way to prove a point. For and, if you imagine this is on my x-axis goes from false to true of variable x, and my y-axis goes from false to true of variable y, then in order to classify, like I can have 4 possible outputs, and that's these circles. in order to classify them into true or false for and, this is the only one that can be true. So I can just draw a line here and say everything above that line is true. Similarly for or, there's only one that can be false. So I can move my line over this side and say everything above the line is true again. So this is something where if you were to represent this as like false is 0, true is 1 on both axes, and you were to represent the two-dimensional point, like anything down here would be false, anything above this slope would be true. The thing with XOR is that you have this problem where the trues are here and like the falses are there, so you can't do it with a single line. There's no way you can draw one line in this diagram and properly partition where your true and false space is. However, if you could take this thing, this piece of paper along the diagonal and fold it over, then you could draw a single line because your trues are right there and you basically like warped the falses back to being over here on one side of the line. So this act of sort of like bending space or folding the paper is nonlinear, because we had a linear space, like a flat piece of paper, and you're having to deform it in some way that you can't do with just like, multiplication effectively. You have to have some sort of curvy thing. And so you can achieve that by using a nonlinearity. Yeah, that's why it's called nonlinear. So what that ultimately means is like with this setup right here, you could train purely this to solve and or fine, because you're able to like output values like on the, it's basically fitting that line and saying, is it above or below? You could not train only this to solve XOR, because like it would always be wrong half the time, right? Unless you're able to do something sort of nonlinear. So that's why we get into the idea of like you have to stack multiple of these together and then put a sort of nonlinear function in the middle. So like, let me, I'll get more to that later, but let me come back over here and look at sort of the next thing. Instead of doing all of this by hand with just these tensors that are floating around, it's useful to think of them in terms of like operations or like the thing that it does. A module is another name for it. Module is what Torch calls it. More generically, you've probably heard these things referred to as layers. So the idea of so we started with a perceptron is just a single matrix multiplication. The next thing that they had in order to solve things like XOR is called a multi-layer perceptron, which is effectively multiple matrix multiplications in series with nonlinearities in between them. So to handle everything we were just talking about of like W times X plus B, that's something that's referred to in PyTorch as a linear layer. If you've used TensorFlow, or if rather more specifically, if you've used Keras, which is another framework for this, they call it dense. They're the same thing. And this is this. I mean, without the tanh, like it's the same exact thing. So if we were to look at this, this takes the number, like the input dimension and the output dimension, just like we had right here. So this is the same thing as our W. And it also, like when you create it, it has what's called the weight, which is the W. W is actually short for weight. Fun fact. And it has the bias, which was our B vector. So like when I created that, you can see here it says in features 2, out features 3, bias true. So then the weight matrix was of size 3 by 2, because it's actually the transpose for reasons. And then the the bias is size 3, which is the same as our output features. So this is exactly the same as what we just made before. It's just a little more convenient. It sort of packages the weights and the biases together. You can also create one of these without a bias vector. So in this case, you can see when I ask for its bias, it says none. So there are, even though when we talk about it, we always say it's like it's, you know, WX plus B, there's not, you don't always need a bias. In certain times, like, yeah, there are times where you don't need it, and then you can just like say false so that it doesn't even have it. But this is the thing that we were just dealing with in specific PyTorch land. So now, getting into that, I mentioned this idea of multi-layer perceptron. This effectively is the minimum that you would need for a multi-layer perceptron. If you've used scikit-learn has a MLP sort of baked in, and it like if you look at the fun, what you need to do is you say the input dimensions, the hidden dimensions, and the output dimensions. So if I define that right here, and I'll get to the rest of this in just a second. Ultimately, what we're doing is we're saying I need a linear layer, which is again a in by out matrix multiplication. So I'm going to give it my input dimensions, and then in this case, my hidden dimensions. It's just a number of dimensions. It's called hidden because it's in the middle. With these things, you have like the input makes sense. It's how big something you have to get. The output is how much you want it to give. And then the stuff in the middle is just referred to as hidden because like you don't directly see it. It doesn't have any explicit meaning. It's just like how big you're making the stuff in the middle. More on that. But so we go from input size to hidden size, and then some nonlinearity. So in this case, I was using a sigmoid. Followed by a hidden by output, and then another sigmoid. So what this will ultimately do is it takes a vector of size input dimensions, converts it into a vector of size hidden dimensions, does some nonlinear thing to it, squashes it, takes that hidden dimension one, turns it into an output dimension vector, does some nonlinear squashing, and then gives you the result. There's this nice convenient thing because most of the times inside of neural networks, you're just chaining these operations together. It's just like a series of matrix multiplications, and you know you can like a matrix multiplied by a matrix multiplied by a matrix. Like it's just like it's like you get a vector, it goes into the next one, it goes into the next one, you end up with a vector. So being able to just chain these together very quickly like this allows me to treat it like one thing. So down here, when I'm actually calling it, this FC is short for fully connected, which is another name for linear. So ultimately, you can just pass in your input. It again goes from input size to hidden size, squash, hidden to output, squash, and then that's what I get. So the rest of this is like just PyTorch stuff. Like there's two things you need when defining a module in PyTorch. You need the constructor in it, and most importantly, you need to call this. Because module does like a lot of stuff for you under the hood. And then you need to define a method called forward, which takes your input and well, will give your output given whatever you're running it through. In this case, it's this little guy right here. So questions, comments, thoughts, points of clarification before I move on. Is it clear that this part is ultimately what we're doing? It's a little annoying to do by hand, so this is a nice way of being able to chain these things together. But it's the same exact operation. So one thing when coming up with this, you have this hidden dim that I sort of like glossed over. Like, what is this? It's a dimension, like however big you want this to be, of something in just the middle, right? Because again, we know what the input size is. Presumably, we have something we're trying to do, and we know what the output size is because we have something we're trying to do. The hidden size depends. It's a hyperparameter. You have to basically guess. You can search for it and stuff, but generally you're sort of guessing. It depends on things like your input size and your output size. Also, a good rule of thumb for things like, let's talk about the image classification thing. We were going from 100, a 10 by 10 image in the input and a 3-dimensional output. What would be a good hidden size if we're doing this? Usually rule of thumb is somewhere in between your hidden or your input and your output size. So 50, sure, seems good. You can change it. It ultimately doesn't matter that much. The bigger it is, the bigger the model is, or it's really the wider the model is usually. When you talk about this, the size of every layer is referred to as its width, and the number of layers you stack is its depth. That's where the term deep learning comes from. With deep learning is effectively when you take more than 2 layers of something, and that's your model. So another good rule of thumb, usually if you have any flexibility, choosing a number that's a power of 2 is good, just because it fits nicer into memory. So it can be more computationally efficient. It's more just like a general guideline. So if I was going from 100 down to 3 in the middle, I could pick 50, like I said, could also pick 64, could pick 32. It again doesn't really matter. Things that are powers of 2 fit better into memory. Cool. So one of the other things here, like so far we just talked about what the operation is. We're doing like linear regression with a nonlinearity. So, but that was just we saw how to run it forward. We can give an input to the model and get an output. The thing that, and you could do that right now with NumPy also. Thing is your values, you'd have to figure out a way of figuring out what your weights would be, like to make it actually do something useful. So the real power there that things like PyTorch, TensorFlow, and deep learning frameworks give you is they have built-in support for backpropagation, which is the way that that we end up training neural networks. So the main things to make it work is, as long as your model is differentiable, like so it's continuous, there are numbers, then it effectively can get sort of backpropagation for free. Backpropagation is effectively the chain rule from calculus. So like you run something forward through the model, you do your matrix multiplications, you get out an output. You compare that to whatever your target is if you're doing supervised learning, and you get the error, right? So I expected a 1, I got a 2. So then what you're ultimately doing is like saying, the difference between those, like its derivative, I want to figure out how to go back and like update all of the numbers inside of my model so that they will give me a 1 instead of a 2 the next time. And since you're training together multiplications and additions, you can just like handle that with the chain rule, sort of going backwards to figure out how update this one a little bit to move it towards that, and then so on. That is all handled for you in these frameworks. You don't want to be doing that stuff by hand. You can to prove that you know how it works, but it's error prone, it's slow, computers are good. So that's one of the big things that these frameworks handle for you. So under the hood, even though you're defining this thing called forward, part of nn.module is the backward pass, or how to update the module itself, is handled for you. Very convenient. So with just literally this little bit of code, you could solve many different problems very easily with exactly the same sort of like training setup that we're going to be getting to. one of the other really nice things about PyTorch, TensorFlow, and other things like that, as compared to NumPy, is they also have built-in support for acceleration, so GPUs specifically. And that's what I'm getting to right here. So since deep learning is effectively matrix multiplication, and we're going to be stacking lots and lots of these, you have lots of matrix multiplication. So really the holy grail of all of this like is speeding, like the faster you can do your matrix multiplication, the faster you can iterate, the deeper your model can be, the better it'll ultimately be, because deeper generally means better. And finishing within your lifetime is also a nice property to have. So one of the things that was discovered is that, so GPUs, graphics cards, their whole, like their bread and butter is to do really fast multiplication effectively in parallel. Because the way that they work, if you've heard of shaders from graphics programming and stuff like that, they kind of go like per pixel, like you give it basically, what numbers do I multiply to get the color of this pixel? That's a gross generalization, but and since the color of this pixel doesn't care about the color of that pixel, I can do them at the same time without having any dependencies, which is nice because if I can do them at the same time and I have lots of little cores doing it at the same time, I can do n pixels in one cycle instead of having to take n cycles to do it sequentially, which is the same exact thing as matrix multiplication, because the multiplication step is totally parallel. You can do all your multiplies at once, and then you just have to wait for them all to happen to do the summation at the end. So, and addition is much faster computationally than multiplication. So this is one of the reasons why like graphics cards, GPUs and stuff have been a game changer for deep learning. And thus all of the frameworks have support for it, which is nice. So in PyTorch, for instance, you'll end up seeing like this line everywhere. You're going to figure out, like, basically if you have access to a CUDA device, this gives you the string CUDA, otherwise it's the CPU. And then you can take this device, whatever you're on, and you can start to pass it to things. You can put your, because really what happens is like at some point everything will start on your CPU. Then you have to basically move it to your graphics card, move it to your GPU, if you're going to use it there. So like your model itself, you're going to send that over to your graphics card. Your data, you're going to send over to the graphics card. Then later on, when you want to use it, after you've done your computations, you move it back. So it's really convenient to only have to specify the device that you're sending it to. So you can specify it when you create something. You can also, right here, using the .to and then give it a device name, you can move it to whatever device you want. And then usually at the end, like if you wanted to say convert a torch tensor into a NumPy array, it has to be on the CPU, so .cpu is also there. Where this comes in really handy, especially in Google Colab, for instance, is up here in the runtime. If you go to change runtime type, GPU is right here. So none means you only have a CPU. This gives you an instance that has a GPU, and this gives you an instance that has a TPU. Currently, the only things that support TPUs are TensorFlow. So, and they're just Google's sort of proprietary version of a GPU. So most of the time, like if anything, you're going to be asking for a GPU instance. If you're like, Google Colab is really nice in that they just sort of give you this compute for free, unless you're paying for Pro, in which case you get more of it and you're paying a little bit. The one thing here is like CPUs, there's almost always a CPU instance available. So like if you're especially just like trying things out, it's much nicer as a person to be using a CPU instance so that you're not eating a GPU one for someone else. If you're using a GPU, like it will nag you to say, are you actually working? Like, are you still doing something? Like, because they're all higher in demand. So generally when you're prototyping, keep it on CPU. When you actually get something up and running, you can do it GPU. I'm going to switch to GPU just to show how this works though. So I switched to my runtime type. Once this connects again, Yes, delete previous runtime. So I'm just going to come up here, and I have to import Torch. Okay, so that's ready. And now in that device block, if I run this, so first of all, for this line up here, when I say print device, it printed CUDA, which means that I have access to a GPU. Right here, I created a tensor, doesn't matter what's in it, and I said I put it to that device. When I print this, it's right here. You can see this device equals CUDA:0. Beyond, like, you can have a machine that has multiple graphics cards, and so if they'd be indexed to CUDA:0, CUDA:1, CUDA:2, so on. Most of the time you're just going to be seeing this, but like if you're talking about big things in like a huge cluster on like AWS or something like that, you can actually, PyTorch will spread out, or it can handle multiple GPUs, which is very convenient. So this right here, this tensor is another random one that whatever, and this one, since it doesn't say device, that's on the CPU. After I say send it to the device, this is the same exact tensor, but you can see it on the GPU. Then, like I said, we can convert things into NumPy arrays, but if you don't send it back to the CPU specifically, then it will throw an error. For instance, if I do this, it will complain, saying can't convert CUDA device into NumPy tensor, use torch.cpu. So that, like, what ultimately, like, it's not that impressive right now. You're saying, oh, you can make it print a string right here. When suddenly, like, a single operation that used to take like seconds or even like minutes goes to taking milliseconds, that's when you really say like, oh, and that's the benefit of using GPUs. And it's just super convenient to do so in a framework like this. Now, so that I'm a nice person, I'm going to turn this back off, which will delete your runtime because you're actually switching to another instance and stuff like that. But yeah, thank you. So, and one thing that, where did I put it? I put a note somewhere in here about like the debugging of, like, once you start doing this. So, okay, let me back up. Doing this specifically of like saying, checking if you have a GPU, and then if not, defaulting CPU is a good practice, because like if I was to say like I can do just like I could do .cpu, I could do .CUDA here, and it does the same thing. This says like, okay, send it to a CUDA device. Right now I'm on a CPU instance, right? Let me start this again. It can be tempting to do something like this, but it will, yeah. If you try and do that on a machine that doesn't have a GPU, you get this error. So by explicitly saying, oh, I'm going to send this to CUDA, you're making it so that your code can no longer run on a machine that does not have it, which is not nice. So the best way to handle it is to do this, and then always like pass around this device variable, send things to device. An issue that you run into, though, especially on a Mac, like I am when you're prototyping these things, if you were not doing this in a notebook, is if you forget to send something to like the appropriate device, and then later on you like just debugging that you have set that all up correctly when you don't have access to a GPU, because like you can't send something from the CPU to the CPU, like it's already there, it won't break. So debugging this can be a little annoying, but still it's better than trying to write all of the GPU integration yourself. I'm gonna leave that at there, and we have a few minutes for additional questions or comments. Anything from anyone?
I mean, I think from
Sorry, go ahead.
when I was thinking about my hyperparameter tuning, I was just like, I should have used the GPU instance in Google Colab. That was my only real thought, but yeah.
Yeah, definitely. You use it. It's good.
Thanks.
Yep.
Sorry, can you actually go over a sigmoid function transformation again?
Yeah, so it's effectively, I mean, this is showing like just exactly what it is. So like for your input values are here on the x-axis and your output is in the y-axis. So if the input to this is 0, it ends up outputting 0.5. As you get higher, like you can say, see a value of 2 is up here probably about like 0.75-ish. A value of 4 is like almost 1. A value of 6 is like really, really close to 1. A value of 10,000 would be really, really, really close to 1. Right, so you're approaching 1 as you get higher. And then as you get below 0 on an input, you're approaching 0. It's symmetrical in both ways, but it's just, it's the same thing as like with logistic regression. You're squashing this to approximate sort of a Boolean value. So that what the model is trying to do, like let's say the model is going to output something on the x-axis here, and then we're going to interpret it through this sigmoid. So if the model is like, I'm really, really confident this is true, it'll output some stupidly large number, and then the sigmoid function will squash it, and it'll be some value really close to 1. And if it's like, I'm really confident this is a 0, it'll output some really large negative number, and then it'll get squashed and end up being 0. If it's like unsure, it'll output something closer to 0, and then it'll end up closer to 0.5.
Okay, thank you.
Yeah, and the I think that makes intuitive sense for the outputs of stuff. Why it matters on the input is because this is, or sorry, not on the input. Why it matters in the middle is because this is non-linear. Like it actually, it does that sort of folding of space that I was showing. I can't click on it in my other tab here. Like the ability to sort of bend your parameter space around like that is accomplished in the intermediate steps of this. So the only way you could do this is if you had a 2-layer model. So like input to hidden, non-linearity, hidden to output. And then you usually use a non-linearity to get the values to be between 0 and 1 or whatever. Yeah, there's some nice animations that I should actually find for you that talk about that show like the transformations that are happening, because like if you're only doing linear things, the only operations you can do is translate, which is like move up, down, left, right, and that's effectively adding a bias. You can do rotate, you can do scale, you can do skew, and that's it. None of those fold. So if you have this problem of you have to draw multiple lines, you can't draw multiple lines. You want to fold space around so that everything's on one side of one line. And that's where the nonlinearity is coming. All right. Cool. Well, that's it for today. We will go through more of this at another time. So thank you all for coming.
Thanks, Cole.
Thank
Thanks,
you.
Paul. Bye.
All right,
Thank
bye.
you.